If you are trying to learn about momentum, this video is the right place for you. We're going to talk about the basics of momentum, and we're also going to do some qualitative problems. If you want to learn how to do quantitative problems, you'll use all of these ideas when you do them, but you're going to want to look to the second video or the accompanying video after this one. We are going to talk about where does momentum come from. We'll talk about what it means for momentum to be conserved, and direction matters. And you'll find out direction really does matter when you're talking about momentum. Okay, well, first of all, where does the idea of momentum come from? Well, we all recognize this, I hope. F equals ma. Okay, well, what if we wrote it in a slightly different way? What if I said force equals mass times acceleration, but instead of acceleration, I'm going to put in the definition of acceleration, which is change in velocity over change in time. Don't be afraid of the triangles. It just means change in. So instead of having to write change in, we just write a little triangle here. And after all, acceleration is how much something changes in its velocity in a certain amount of time. Okay, now let's employ your algebra skills, and I'm going to multiply both sides by change in time. Cancel, cancel. What do we get? We have F times the change in time equals m times the change in velocity. All right, well, you might have noticed from your studies, or maybe if this is your first look at it, momentum, which I know we're saying that P stands for momentum. I have no idea where that comes from, and I haven't read anything anywhere that explains it, so just accept it. When you discover something, you could name whatever variable you want for it. But momentum equals mass, waiting for the internet to catch up with me here, mass times velocity. So change in momentum is mass times the change in velocity. So this portion is the change in momentum, and we'll work with this equation, or actually this side of the equation, a little bit more in the next few slides. And this happens to be actually a very useful expression, and we're going to name it impulse. And we will talk about this as well. So, impulse equals change in momentum, and you're going to be hearing these words. All right, and we say that there is a change in momentum in a system if an external force acts on it. So you might ask yourself, well, what the heck is a system? Well, a system really is the set of objects that you're talking about. So you're going to notice that when we're talking about momentum, you're going to have a lot of things colliding. You're going to have things hitting each other, all right? So if I had two boxes and they were to collide into each other, those boxes would be in my system. I could say that the boxes are on a table, and the boxes and the table are my system. So a system is going to get defined when you have a problem, and it's usually just the objects that are moving in the system, or not moving, or the objects that are interacting in the system. So that's what that is, and you'll get a better idea of it when we start to do problems. Okay, let's stop talking in the abstract and let's talk in a little more concrete terms. All right, so in which case is more momentum lost? So in which case is there a bigger change in momentum? So here's the situation. We have two identical balls, and One is thrown at a wall and it bounces back with the same velocity. So we're going to assume that no thermal energy is lost. So in essence, it's moving with an initial velocity of v naught, and it's coming back at the same speed v naught. But when you talk about momentum, direction is a biggie. You have to pay attention. So we're just going to go for, in a number line, this is the positive direction, this is the negative direction. So we're going to say that this is moving right after the collision. So right before the collision, it hit with a velocity v naught or v0 or v original, whatever you want to say, and then immediately left the wall at negative v naught. The second situation, same ball, same mass, identical, and it is just hitting the wall at v naught, but then it just sticks there. So imagine that it is a ball made of clay, say. And so the first one was a rubber ball, same mass, same size, all the same things, and it bounces off the wall. In case B, that same identical ball of clay is going to hit the wall at v naught and then just stick there. So its final velocity was essentially be 0 meters per second. All right, so this is the question: which one, in which case, A or B, is more momentum lost? So I want you to pause the video, think about it, and make a guess. And seriously do this. You learn more when you invest more. So pause the video and make a guess. All right, I'm going to assume that you pause the video and you have a guess going. So let's see, what would its change in momentum be? All right, well, we initially said, and you know what? I am going to change, I want to change the color to black. I just feel like writing with black ink right now. Okay, so in A, we have our change in momentum, which can be written like this, right? This is the change in velocity. And whenever you see this change in, that means the final minus the initial. So in this case, it's the final velocity minus the initial velocity. Okay, so in order to find the change in momentum for A, the final velocity is negative v naught. So it would be negative mv naught. Okay, so I'm doing the distributive, multiplying now. And minus, and what's the initial velocity? Well, it's going in the positive direction, so it's minus a positive m v naught, which really is just minus m v naught, and that would be negative 2 m v naught. Okay, so its change in momentum, the magnitude, is 2 mv naught. Okay, now for B, in situation B, what would its change in momentum be? Well, what's its final momentum? It's not moving, so the final momentum would be 0. Minus, what's its initial momentum? The same as in A, mv naught. So what would the total change in momentum be? Oh, that would be only negative mv naught. So if when looking at the magnitudes, ball A had a greater change in momentum, or twice the change in momentum that ball B did. Now, I'm guessing that a lot of you said, well, B would have the bigger change in momentum. And that's because we're thinking, well, look at this. The ball flew into the wall and then it just totally stopped. That's a huge change in momentum. Well, think about this. In situation A, not only when the ball hit the wall did it have to stop, momentarily for a very, very short moment, but then it had to rebound off of the wall. Now, you could do a little thing, you could do it like a little experiment or whatever to give yourself a more intuitive feel. what you can do is you can get something that you could just toss up into the air. So a ball, something soft, something light, pencil case, something like that. And what you could do is you could at first throw the ball up, and then when it hits your hand, have it stop. Okay? But now I want you to throw the ball up, and when it hits your hand, hit it so that it bounces off your hand right away. You're going to notice that you're going to feel more of a force on your hand when you have to do that. And that indicates, as we're going to see in the next slide, that you're going to have more of a change in momentum. All right, so bottom line, you want to really pay attention to direction when talking about momentum here. And change in momentum is final momentum minus initial momentum. And if I were to add something here, maybe I should have done this in case you got lost, but this is the final momentum minus the initial momentum. Okay, let's test your knowledge of the last slide. I'm going to give you another question. Two identical boxes. All right, box A and box B. And just for clarity, let's label these. This is box A, and this is box B. Okay. They are going to have two balls, just like in the last situation or whatever. Hit them. One is going to bounce off at the same velocity as when it was hit. The other is going to stick. Which box ends up moving faster to the right? So you're going to pause this for a second and you're going to guess. Okay, I'm hoping that you picked A or B. And, well, in which case is the box gaining more momentum? Is there going to be a bigger change of momentum of something bouncing off of it or something just hitting it and sticking? Well, if you picked A, you picked the right one. There's a bigger change in momentum when balls bounce off something. And this is going to result in a bigger force on A, and A is going to move faster than B. All right, I've mentioned the word impulse in many slides, so let's talk a little bit more about impulse. Now, as last we heard, when we took our F equals ma equation and changed it around a bit, we saw that this is the change in momentum, and this quantity is the impulse. If you were to look in your book, you would see graphs that look like this. This is going to describe the force of something hitting another object. So in this case, let's take, for example, when the ball hits the wall, all right, this is going to be the force that it hits the wall when it first starts to hit the wall, and T is going to be the time of impact. So when it first hits the wall, the force is going to be small, and then the wall is going to end up stopping it, and then the force is going to decrease. And this time period is incredibly small. Come on, here, work with me here. That delta T is going to be very, very small. All right, so when I was first learning this, I was always trying to, you get the impulse problems, and you're like, okay, well, I'm going to have to use this graph and trying to figure out how you could, use this graph to solve problems. And really, you can't use this particular graph to solve problems unless you do some integrals. And many of you are not in AP Physics C, where you have to worry about calculus just yet. So what if I made another type of graph? All right, so I'm still going to do force versus time, And we're still going to make this a very short time interval. So delta t here is very, very short. But say we consider that this is like the average force. And in a lot of your problems, they're going to tell you that you're going to have an average force of something. They do this for a reason. An average force means that you're just kind of taking the average. So it would be maybe about, this would be the average force if you were to average the forces out throughout the time period. And what happens if you take a little, well, what happens if you took the area of this whole thing? What would the area be? Let's say it's a square. So this is going to be the force. This is your change in time. Oh, wait a minute. What is force times change in time? That's your impulse. The area under the curve is equal to the impulse or your change in momentum. Remember, if you watch those pattern in physics videos, whenever you get a graph in physics, you are either going to look at the slopes or you're going to look at the area under the curve. And especially if they give you a nice, simple geometrical shape, chances are it's going to be the area under the curve. So always look at that. So for example, if they give you a graph in a problem and they ask you what a change of momentum is, note that your force times your delta t is equal to change in momentum, and that is going to be the area under the curve. Okay, well now we're going to look at some momentum situations without numbers. We're going to concentrate on the concepts. I do want to go back and state that when we were talking about this system, you know, how we had a ball bouncing and then rebounding off the wall, our system would be the ball that's bouncing back. All right, and the wall is exerting an external force. So that external force is going to change the system's momentum. And we saw that the change was 2mv naught. All right, here when we are going to talk about our truck and a big fly colliding, okay, the truck and the fly are our system. So this is a very common problem, and you're going to get various things colliding into each other. If you see a collision problem as a physics problem, your brain immediately wants to go to momentum. So if on the AP test or on your chapter test, if you see that two things are colliding, immediately think, how can I use momentum to solve this? Or how could momentum be a part of the solution of this problem? So to see if you totally understand and get an idea of what momentum and impulse are, I'm going to ask the question here, okay? So we have a big semi-truck and it is barreling this direction. We have a little teensy fly and it's going that direction. At some point, that poor fly is going to hit the windshield of the truck. And I am going to ask you who experiences the bigger change in momentum and who experiences the bigger impulse. All right. Well, let's see. In this problem, we really weren't given anything. Well, we want to know change in momentum. So normally what you would do is you would go and you'd say, okay, well, my change, what's going on here? My change in momentum equals delta V. But they didn't really tell me the velocities. I don't really know anything about the velocities here. So I can't really figure out my change of momentum using this. But what is my change of momentum equal to? Oh, it's also equal to the impulse, isn't it? All right. So do I know anything about the force that upon impact? What about the force on the truck compared to the force on the fly? Now, you have to go back to your knowledge of Newton's laws here. Your intuition wants to say, well, of course the fly got hit harder, but Newton's shaking his head saying, So what is the sure sign that you could figure out if action-reaction forces? That would be if you could say A puts a force on B and B puts a force on A. If you could say that, then the forces are action-reaction forces, which means they are equal. So we could say the fly puts a force on the truck and the truck puts a force on the fly. Therefore, these forces are action-reaction forces and they are equal. So the force that the truck puts on the fly and the force the fly puts on the truck are equal in both cases. So you have the same force on both. And delta t, that's the time that they collide. Well, is it possible to have a collision where one object collides longer into the other one than the other? No, that's just not possible. If you have a collision, if your two fists collide or your fist hits your hand, your fist, the closed fist, is in contact with your open hand the same amount of time. So in this case, there is the same force on the truck, same force on the fly. The change in time, or the collision time of the truck, is the same as the collision time of the fly, which means that the impulse of the truck is the same as the impulse on the fly. So, an impulse equals the change in momentum. So, who experiences the bigger change in momentum? Neither. They both experience the same change in momentum, which means they both experience the same impulse. Now, you do not, I know in your brain you want to think impulse sounds like impact, but they are two totally different things. The force of impact is your F. Impulse is your force times your collision time, okay, or your change in t. So don't get them confused in your brain. Just because they both start with IM doesn't mean that they are the same word with the same meaning. All right, so whenever they ask questions like that, you want to ask yourself, okay, change of momentum. That means I need to know something about their velocities. If they don't tell you anything about the velocities, then go to the second definition, if you will, above change of momentum, which is impulse. Do you know anything about the forces? Do you know anything about the collision times? You may not know values, but compared to one another, you can say, well, I know the force on the truck is the same as the force on the fly. Collision time of the truck is the same as the collision time of the fly. Therefore, they have the same impulse. Therefore, the change in momentum is the same. This is a complicated idea to wrap your head around. So, if I were you, I would go back and just repeat the recording of the slide, just until you could get it into your head, and then explain it to yourself. If you get stuck in the explanation, then play the recording again, listen to the ideas, listen into the reason, and then you're going to be able to fully understand it. You're going to be able to fully grasp it. Okay, here we're going to look at a different problem. All right, we have person A and person B, and they're smiling because they're listening to a physics video. And person 1, now they are identical twins, identical in every single way. Mass, velocity, they're both going to hit the brick wall, and they're going to hit the ball, the biggest ball of yarn, with the same velocity. All right? And we want to know who experiences the bigger change in momentum and who experiences the bigger impulse. All right? So, for this one, well, let's see. For this one, and I might add that the brick wall is going to stop person A, and the biggest ball of yarn is going to stop person B. All right. And they are each moving at V0. All right. And when something stops something, after the collision, if this person is stopped, then we know the final velocity is 0 in both cases. All right, so let's see. Who experiences the bigger change in momentum? Well, if we go about, change in momentum is m times the change in v. Okay, so change in momentum for person A is going to be whatever his mass is, and they both have the same masses. Remember, they're identical. And it would be VF minus V initial, correct? So we have m, change in momentum, is equal to, 0 is the final velocity, minus V naught. So that would be negative m times V naught. The change in momentum for the person hitting the biggest ball of yarn ever is going to be, well, the final velocity is 0 minus the initial velocity is the same. Wait a minute. They both experience the same change in momentum. Well, what about the impulse then? Oh, wait a minute. The impulse is equal to the change in momentum. So if both experience the same change in momentum, then both experience the same impulse. Which one, I'm going rogue here, which one, A or B, experiences the bigger force of impact? Well, why don't you get out of your physics selves and ask yourself, would you rather be stopped by a brick wall, or would you rather be stopped by the biggest ball of yarn? And my guess is that you would rather be stopped by the biggest ball of yarn. Why is that? Well, that is because it's softer, right? The ball of yarn is softer, and so it's not going to hurt as much as if you were to run into a hard wall. So then you might ask yourself, well, wait a minute then. The impulse is equal to, and let's make this a different color so we'll make it green. The impulse is equal to force times change in time. So if this is a bigger force, and this one has a smaller force, and we know that they have the same change in momentum, which means that their impulses have to be the same. Well, if we're multiplying a bigger number by delta t, and we have to get the same number as a smaller force times delta t, this would mean that our collision time is smaller here, which means that it is stopped very quickly. And that means you are going to get hurt more. Anytime you are stopped really quickly, it takes more force to stop you that quickly. Here, when you're hitting the ball of yarn, you are stopping, or person B is stopping, not you. Person B has a little more time to stop, a little more cushion. This is an important fact. We use it every day. The car industry uses it when it thinks of airbags. Would you rather be stopped by a very, very hard steering wheel and dashboard, or would you rather be stopped by a soft, squishy airbag? Chances are you would want more time to stop so that you don't have to you don't get as much force placed upon you. So that's the whole idea of the airbag. You don't have as much force on your face when you have more time to stop. Think about it. You would never dream of jumping off of something and locking your knees. The more time you have to stop, so meaning if you were to jump and you were to bend your knees in the process of stopping, that gives you more time to stop, which means you could use less force. If you had to stop someone running towards you, if you stopped them really quickly, you would have to use a lot more force, right? Then if you were given a lot more time to stop them, then you could be a little bit easier and, not use as much force as quickly. It's the whole idea of this. And this is why the idea of impulse is a big deal. If you've ever done in your classes, like the egg drop, building something, you want to build a contraption that compresses or allows more time after impact to stop the egg, because that means the more stopping time, the less force is going to be put on the egg, and your egg is going to survive. This is the whole idea behind impulse. All right, you have made it. You have made it. So I want to just say a few major points here. In the very first slide, we saw that a change in momentum, not momentum of a system, but the change in momentum and impulse are the same thing. Momentum is very direction dependent. You really have to worry about direction. If you get a force versus time graph, the area under the curve is equal to the impulse or the change in momentum. If two objects are colliding and the force on each is the same and the time of impact is the same, then the change in momentum is the same. So that means if two objects are colliding into each other, that means that the forces on each other are action-reaction, which means they're the same, the impact time is the same, and so the change in momentum is the same. Lastly, the momentum of a system is always conserved, meaning it doesn't change unless an external force acts on it. We're going to talk more about this in the next video. And the next video is going to have more qualitative problems, which are going to look like problems in the back of your chapter or in your computer, in your computer programs that you use when you're solving physics problems. And as usual, always remember, hardworking scholars can do anything, especially you Schuler scholars.